Hello, and welcome back to the Clever Cow podcast, where we discuss innovative ideas and work to create a more sustainable dairy industry. This podcast is produced by the University of Idaho ISED grant. ISED stands for Idaho Sustainable Agriculture Initiative for Dairy, and it is a $10 million grant awarded by the USDA in an effort to create dairy manure solutions that are sustainable and economical. I'm your host, Savannah Nunez, the ISED Director of Media and Communications. Today, we have a fascinating episode lined up with an expert who is converting dairy manure into biodegradable plastic. Joining us is Dr. Erik Coats, an engineering professor at the University of Idaho, along with his graduate student, Brandon Boyd. Dr. Coats and his team are breaking new ground with a process that transforms dairy manure into a biodegradable plastic called polyhydroxyalkanoate, or PHA. This process is a pivotal point of the ISED grant's effort to innovate waste management and boost sustainability in the dairy sector. In this episode, we'll delve into the process of how dairy manure is converted into biodegradable plastic. We will also discuss the environmental advantages and the potential economic benefits this could have on the dairy industry and beyond. We talk about biology, chemistry, poop jokes, machine learning with artificial intelligence, public perception, and if the plastic actually smells like manure. So, without further ado, let's jump into the world of sustainable innovation with Dr. Erik Coats and Brandon Boyd. Welcome, Erik and Brandon.
My name is Brandon Boyd. My background is I am a civil engineer. I graduated here at the University of Idaho, Moscow with my undergrad. And I got picked up by this lovely fellow to be in his graduate program. And I'm just currently working on the production or optimization of PHA production.
Okay. I'm Erik Coats, a professor here in the Department of Civil and Environmental Engineering. Bachelor, master's, PhD in civil engineering. Actually a Idaho alum as well from 90 and 94. So, and an Idaho native.
Awesome. Well, it's great to have you guys on the show. You're turning dairy manure into biodegradable plastic. Tell me a little bit more about the research side of that.
Okay. My wife likes to refer to it as pooped plastic. So it sticks in her brain.
We're now going to refer to that the rest of the episode.
Yeah. The technology itself, I mean, you've got what sparked our interest dates back to my PhD program. I was recruited, ended up doing my PhD at Washington State University. My major professor recruited me to do bioplastics and left me with basically a blank slate to figure it out and finish that work, and had the opportunity to hire on here as in a professor position, and wanted to continue that research. It was super interesting along with some other stuff we're doing, and just saw a great opportunity to continue that here in my faculty position at the University of Idaho. Overview, I guess we got a separate question about the process itself, but the technology, why dairy manure, I suppose, is why a lot of people wonder. This bioplastic, Brandon mentioned PHA, the polyhydroxyalkanoates, which is the scientific term for it, but it's just a biodegradable polymer. It's carbon-based. So if we're going to make something out of carbon, we need a lot of carbon. And dairy manure, it's significant quantities of the waste in Idaho and in the region. And it's a waste that needs better management strategies, and there's a lot of carbon. So dairy manure just made sense.
So there's different types of biodegradable plastic. How is yours specifically made? Like, what's the process behind transforming dairy manure into biodegradable plastic?
Let Brandon kind of walk through the overall technology first.
Okay. So it's essentially just a 3-step process. It is involved, but it's not at the same time. Going from the dairy manure, you need to break it down so the bacteria that we use to produce the PHA can utilize its key components, such as the carbon, like Dr. Coats mentioned. So we have a fermenter that takes the manure and ferments it, breaks it down into simple carboxylic acid. So like acetic acid, like vinegar that you have at home. But it's just simply, we take the manure and we get it broken into acetic acid, propionic acid, kind of short chain acids. And then we can take that and feed it to what we call an enrichment reactor. That is just enriching for different bacteria. There's bacteria all around. Some of them can produce PHA, some of them can produce methane. But we want to enrich for the PHA producing bacteria specifically. And then the last step would just be the production, where we take some of those bacteria, we put them in a separate reactor, and we just continually feed them. And they can turn those VFAs into PHA through just their normal processes that they use to live.
I toured one time a wastewater treatment plant, and kind of similar to that process, it seems, where like you're starving and feeding the bacteria to get this product, the PHAs. Is that basically how it happens?
Yeah, I would say for wastewater plants specifically, they don't so much do the what we call the feast-famine cycle, since they're always receiving influent. They are just always kind of feeding when the availability is there. But for our PHAs specifically, we do let them eat and then famine off and then feed them again and just repeat that cycle.
And Brandon, how long have you been on? I think you might have mentioned it at the beginning, but...
Oh, no. I just completed my first semester back in the fall of 2023. So I'm just moving into my second semester with Dr. Coats here.
And then, Erik, how long have you been?
Since 2004, maybe 2003,
Oh, wow.
2004. So started more on the municipal side. Landed here in 06 as a faculty and embarked on the dairy pathway. A few years later, we've looked at crude glycerol. There's Brandon mentioned this feast and famine, as you indicated. That's how we condition bacteria to do this. And to the bacteria, I mean, of course, it's not plastic, right? It's a carbon source and it's an energy source. That's what the bacteria see it as. If you're a bacterium that can store carbon, you're advantaged over bacteria that cannot in times of when food is limited. And so we just leverage that metabolic capability in our enrichment reactors, as Brandon mentioned. And then, and so we've explored different carbon sources. So others in the region, amalgamated sugar has an organic acid-rich waste stream that could blend in well. We've looked at municipal wastewater, tomato cannery wastewater, really any organic-rich waste stream that either already has these organic acids or can be fermented to produce organic acids is amenable to the technology. So it's got some universal flexibility, if you will.
So one of the most exciting aspects about the biodegradable plastic is the environmental impact that it has. How does this process contribute to sustainability and environmental stewardship within the dairy industry?
We see it as kind of impacting both the dairy industry and the environment in several ways. One, obviously, for the dairy industry is land application. I mean, especially here in Idaho, in southern Idaho, they face issues where they over-apply, and you see phosphorus and nitrogen being leaked into the groundwater. And obviously, that is a huge issue. But also, the current way that we store the dairy manure is just in lagoons. And that can lead to methane being off-gas just directly into the atmosphere, which obviously is not something that you hope for when thinking about the environment. But another major issue is traditional plastics. You hear stories about a bunch of plastic being left in the ocean or landfills, and it creates substantial issues, the water quality or land quality for what you're trying to do. So having something that's biodegradable and after a year, 6 months, 2 years, it's essentially gone. It's not there anymore. It would be a great product to utilize to help combat the fossil plastics that we use. We could control methane production that we use in lagoons. And obviously for the farmers, you're not going to be hit with any fines or anything if you're over applying, because you have this second way that you can use your dairy manure.
Yeah, definitely. And to be able to get more money for that manure, like to increase the value, is going to be huge, I think, for farmers. We've talked about this previously in some of the other episodes, but in a dense dairy region where there's a lot of manure around, you have to ship it farther and farther to find soil that you can apply it to, and it costs a lot of money to do that. So to be able to have a different opportunity to send your manure and turn it into bioplastic, have a different outsource and get more money for that is an extreme advantage.
And if I could chime in there, I mean, we know, I mean, the dairy industry is keenly aware of environmental impacts and is very concerned about mitigating as well. So this is it is a partnership with the dairy industry, and they're looking for good solutions, right? That would allow them to upgrade, upcycle, recover value from the manure. And as we were talking about before we started, you're coming from a dairy family as well. I mean, it's tenuous, right? The margins are thin, and if there's an opportunity to pivot from inputting costs to deal with this waste, and as you said, the challenges of having to move it long distances to agronomically utilize it to one where they're generating value. It has some real value for the dairy industry, and it dovetails with, I think, what the industry is trying to do. They're trying to get to this net zero. I mean, there's a big push in the dairy industry, net zero emissions, really proactive on the environment as well. And I think we dovetail really well with them. One of the things that I'm just mentioning now, we've also discovered that our process captures, it concentrates phosphorus. And, way I've always sort of seen the challenges in these dairy dense regions. The food to support the dairy is being grown on, large, vast acres, right? And then it's concentrated through the cow. How do you get it back? How do you get it back out to that same acreage, right? That densification of carbon, phosphorus, nitrogen is a challenge. And I think we end up dovetailing nicely with the initiatives that the dairy industry is trying to achieve as well in terms of, reduced environmental footprint.
Biodegradable plastic is very exciting. Through this job, this is my first real exposure to it, besides seeing it, in various places in stores and stuff. So your prediction, I know this is kind of hard to do with the beginning stages of the research, but now that things have been kind of going and tested, your manure made bioplastic. What are you predicting? Like, how long will it take for it to fully decompose in the environment?
That depends on the environment. So if we made this table out of our bioplastic and we have no water, we have no moisture, this table could last decades.
What if it was like just outside?
Sure.
In the field or something?
Months to early years, depending on how we may have modified the plastic. So in terms of products, and Brandon and I were chatting earlier, we could maybe potentially make films. We're collaborating with our Armando McDonald here at the University of Idaho. He's a polymer chemist to possibly to how do we purify the plastic and make films, and maybe we could make films that would be useful in the ag industry, right? Well, a film would potentially biodegrade in a reasonable time frame. I don't want to put a time to it. So.
I guess that's kind of hard, to say.
It really moisture. You need moisture and bacteria because the polymer itself is a food source for the bacteria, and so they will biodegrade it in the environment. But if we lacking moisture, certain applications it could last a long time. But if you wanted to biodegrade rapidly, it could be months.
Yeah, and I think how it goes with typical biodegradable plastic is sometimes we'll have certain places where you'll discard those and then they put it in a different environment where it can break down faster.
Yep.
With more like just a more controlled setting.
And looking at probably maybe decades in the future, assuming this PHA achieves some sort of commercial viability, some sort of recycling, right? We would want those products back into our factory, right, to be fermented, right, and right back to PHA. So it could be. You mentioned visiting wastewater treatment facilities. Brandon and I are pretty active in the wastewater industry in general, and professionally, it's all about the circular economy. Right? So how are we recycling, upgrading, raw materials of value in the waste stream? And dairy manure and bioplastics is just part of that equation.
Definitely. Building off of that with like the dairy bioeconomy model, I had this crazy idea. It might not happen, but so it would be just really cool to see, your biodegradable plastic made from manure somehow cycling back into the dairy industry and being used for, I don't know, like single-use plastic, that packaging, whatever. But even I had the idea, so with silage pits, we use a ton of plastic to cover them. Depending on the environment, if the projection was that it could last a little bit longer and not decompose, because usually it's on there for like a year or so. If it was able to last that amount of time and cover the pit and do all the same jobs and kind of ferment just like normal plastic does, that would be an incredible opportunity, I think.
Agreed.
I think it would be a great opportunity as well. But going back to what he said about different environments, I think it would be kind of depending where you're at in the country. Because if you're somewhere like the coast of Florida or something where they're getting hit with hurricanes and stuff, I think that would probably get more. It would be a more tenuous environment on the bioplastics and
wet, moist.
Oh,
well, sure. Yeah, but if you also have like hurricanes or stuff that's tearing it apart when it's in smaller pieces, it is going to degrade faster and everything.
I feel like it probably, I mean, so far it seems that this kind of project is going to work in Idaho and then work its way out. So I think maybe in southern Idaho, since it's a little bit drier, the weather's decently moderate since it's so desert. I don't know. I would love to see that happen. And I know a lot of people would get excited about that, especially dairymen, and I think ultimately they're probably going to go with the cheapest option, but I don't know how it would stack up compared to normal plastic.
And when the cheapest option, there's, if they're not having to dispose of plastic that they're using, I mean, that's a cost there. So it all depends.
Definitely. You have to weigh that for sure.
Yep.
So every research project has its challenges. What obstacles have you both encountered, and how have what? Are there many? And how have you basically addressed those moving forward?
Well, me personally, although I've been here a short time in the grand scheme of how long Dr. Coats has been trying to get this to go forward, process control is a very key issue that we're trying to combat. So optimizing the process, trying to get the most out of our VFAs that we're producing. Obviously, you don't want to, especially if we scale up the process.
Sorry to interrupt. So PHAs and VAs?
VFAs?
Or
I haven't defined that one yet.
Yeah, you got to define.
Yeah, sorry.
Not that the average person will not know.
VFAs are volatile fatty acids. So they're like the carbon, the vinegar that we mentioned earlier. Yes. Those are VFAs. And they're just what we use to feed the bacteria so they can produce the PHA.
So it comes out of the fermenter.
It comes out of the fermenter, yes. But being able to tell, just in our scale, our batch reactors upstairs that we use for this research, being able to certainly say they've consumed all this food, we need to give them more. That's been very difficult to pinpoint and say, yes, that at this time they've used it all.
Yeah, that does seem really hard to measure.
Yeah. How do we fatten them up? How do we? Yeah. It's basically how do we feed them at the right pace without overwhelming them metabolically, but knowing when they're hungry again, so they'll store more.
Yeah.
Do they? I don't know. Usually, do you see them giving off different signs that they're hungry again? Do they just start dying? Is that how you know?
We're trying to figure that out.
Yeah. We've had a few different ways that we've tried to do it. One was our enrichment reactor, our second step. We just take samples throughout time after we feed them. And then from the data that we get measuring the BFA concentrations in there, we can say, hey, if they've ate this amount over this much time, we get a rate that we can use. And since we're using that culture to prime our production reactor to produce the PHA, we kind of take that rate and put it over. But it's a little difficult because obviously it's a mixed culture. It's changing throughout time. So maybe what you had before is not the same as what you're using the very next day. But it's just hard to try and for certain say, hey, it's time to feed them. We need to fatten them up more.
And I'll add in a little bit there to mention a mixed culture. I mean, it is not only are we dealing with a complex waste stream, right? The fermented dairy manure, which we try to tightly control operation of our fermenter, but there's still a plus or minus. We're dealing with mixed culture. So it's not genetically modified. It's not a pure culture. These are bacteria that we could get from the soil that we choose the wastewater treatment plant. But by and large, they're soil dwelling organisms, right? And the population does shift over time. We've done some molecular biology. We know the population shifts. So it's but maybe 10 different species of bacteria are there, and their relative fractions will change over time. And they have slightly different metabolic capabilities. So as Brandon was noting, the rate of removal, day to day may change a little bit. So if we're trying to operate today based on what we observed yesterday, well, it may not be quite perfect. So I don't know if you want to talk about your machine learning piece.
Oh, yeah. Something we have very vaguely brought up last week. Matter of fact, he just dropped this in my lap.
Yeah, but Brenda's going to have it done in years.
Yeah, obviously. The continual requirements of my thesis are mounting up. But we have all this data that we have. We have VFA data, we have PHA data, dissolved oxygen, redox potential. It's all data that we have, and we've been trying to look at it and try and find a pattern within that data. Like you said, the signs that they give off, just the different measurements. But some things, just how we are biologically, I guess, we're not prone to observe. So we're going to try and implement machine learning and feed all this data to some AI, some algorithm, some pre-packaged software. And our hopes is that if we can look at our data and say, hey, these are kind of the signs of when the VFAs have been depleted, we can utilize that. So in real time, when we're doing a run, it'll start to notice those signs itself and alert us, or we'll have it hooked up to some pump or something that can feed it automatically. And just hopefully the process control part will be more manageable, because we're outsourcing it to some software that is more reliant than us being 70 minutes.
Yeah, definitely, especially for scaling it up later into the industry.
Yeah.
I mean, that's going to be really necessary, because you can't have somebody just monitoring it constantly like you could. But I mean, the amount of money you'd spend on that, and then would increase the price of the plastic. So,
yes, most definitely.
So to make it automated would be the best.
You're probably familiar, coming from the dairy industry, of anaerobic digestion and bioenergy, right? Which, sure, we can do anaerobic digestion, and it's a stable process, but the economies of it make it difficult to deploy into the dairy industry.
Yeah.
With power prices in the region, right? And so, if we can develop a machine learning strategy, train a machine learning model, train a model on our data, and then translate that into, real-time, process control. I think that's a year from now, I think we're going to be in a really, really good place. And then, of course, Colton, who is unfortunately not able to join us today, in terms of challenges. So one of the things that he's tackling is more on the molecular biology side. So he's going at the technology, at the process, specifically targeting at the process at a genetic level. So how many we can measure the potential for a mixed culture of bacteria to make our PHA based on how many of the producers are there, right? So if there are 10 bacteria, there are 100 or 1,000, it's obviously in the millions, but when we talk about, bacteria,
Mm-hmm.
but we're just finishing up a 4-week run. We got a pile of data, and Colton's going to be translating that into hopefully some additional knowledge that maybe feeds into machine learning. We don't know. Right. So there's elements of that we still need to sort of flesh out and see how it's going to, what it's going to tell us. So it's sort of marrying machine learning and all this analytical data we can get from probes with some molecular data.
That's really cool, though.
Not that we would use like ChatGPT, but there's these AI machine learning software packages out there that are available, right? And so there's different statistical methods that you can employ. We're still it's a work in progress.
It's very surface level right now. Like I said,
it's a great
dropped
idea
me on this like last week. So
oh, okay.
he said,
so very entry.
he said, "Hey, how about we try this?" And I said, "All right, we'll give it the old college try."
Well, yeah, I mean, I think that's a great decision for this.
Yeah, no, it's hopefully our hopes is that it works out because, I mean, like you said, process control, especially scaling up, is very important. You want to, I mean, maybe in our batch reactors, if we leave 1 milligram per liter, I mean, that's only 2 milligrams. But if you're getting into large scale industrial, hundreds, thousands, maybe tens of thousands of liters, that's going to be a lot of leftover that you're just wasting. And yeah.
So have you guys made any products with your plastic yet? Or like what have you kind of played around with the different products that you plan on making or that you can make with this specific kind?
So working with Armando McDonald again in our College Genesis Resources, he's been able to purify it. We have, I don't have it with me, but we have some material that, if I was to show it to you, you would think it would be a Glad baggie, right? So it's clear. And perhaps I should maybe back up a little bit.
If some of you don't know already, you can make bioplastic from tons of different things like sugarcane, algae, biomass, plant oils, bacteria fermenting, and like Dr. Erik Coats mentioned, starch from corn and potatoes.
So when we talk about our PHA, I mean, one of the nice things about it as a bioplastic compared to like starch or polylactic acid, some of the other bioplastics that are out there, it's the one that has it can replace, PHA can replace more of our conventional petroplastics than any other bioplastic that's out there.
Oh, wow.
It's got material characteristics very similar to polypropylene, very similar to polyethylene. So it's a direct replacement for petroplastics, whereas polylactic acid and starch are not. Polymer itself that we make, PHA, or the bacteria make, the chemical characteristics, the chemical structure itself is just really similar to petroplastics. That's what sets it apart.
So I've heard a rumor that it's cheaper than some other kinds of plastic. For example, biodegradable plastic made from sugarcane. And how does it stack up for the consumer when they're going to look at different kinds?
The economics, we're working on the economic side. I can't put numbers to that. Where we're advantaged in our PHA technology is we're using free bacteria, right? So we're not having to, we don't need to worry about maintaining, sterile conditions to avoid contamination of our bioreactor because it just in and of itself is contaminated, right?
Yeah.
It's just a mixed culture of bacteria that we literally could inoculate from the soil, right? So, essentially that's free. We don't need to genetically modify it or maintain anything. And so even reactor operations, we're less stringent. So there's a money savings. And then, but potentially the feedstock is free, right? Mm-hmm. I mean, the manure, just, dairy farmers not needing to pay for the management of manure, just here, take it, it's yours. However that might, transpire, the raw material that goes into our process is potentially even completely free, right? So those are huge cost savings compared to PHB, which is one class of our PHA, is produced with genetically modified bacteria and corn sugar, right? So a lot of energy goes into producing corn sugar, maintaining sterile conditions for the bacteria. We don't require any of those things. So huge cost savings in the substrate and the reactor operation that should bring the price down quite a bit.
Your bioplastic from manure, it does have the potential to create an entire new revenue stream, like entire new market, and provide tons of new jobs. So I know you're not an economist, but what are your predictions for the impacts of the bioplastic?
I don't know that I want to be in the prediction business, and yeah,
it's hard. Yeah.
I just remember, several years ago, we were talking to a senior executive on the beef cattle side. He made the comment to me, and this is, his world, that there may come a time that bioplastics production, our PHA technology, deployed into the beef cattle industry, the products of value, that the business is driven by the economics of products made from the waste. And oh, by the way, we also produce beef, right?
Oh.
So, and that's not my perspective. That was coming from somebody in the business, right? Would that be the case in dairy? Even if we could get to a point where we'd run some numbers several years ago that almost showed an equivalent. They talk about dollars per cow, right? Some of our preliminary numbers showed equal amounts of gross revenue on the bioplastic side as producing milk. So
that would be crazy.
It would,
imagining a world where people are raising cattle to create manure instead of milk for the sole purpose to make plastic for the world. I mean, that's
right?
wild, right?
It's wild to think about it, but the more we embrace technologies to recover value from waste streams, it's just going to be a better world to live in.
Yeah, definitely. Definitely.
You want to talk about products a little bit? Like what we think are some products when we...
Well, I asked that. I thought you guys were going to get into okay, here.
So my vision, here's my vision. And I don't know, again, I'm not an economist, right? But what I would like to see, and I've been pushing us to try and explore, is producing planter pots, right? So
I've talked to people about that.
You go down, you go down to the nursery, you buy a tree, you buy a shrub, right? And you come home or you buy flowers, right? You come home and you're planting your flowers, and now you have this pile of, some of it's these really rigid, polyethylene pots, right? Some of them are the really flimsy, probably low density polyethylene, plastic containers, right? But you put that in the dumpster and off to the landfill it goes, right? I mean, that's oil, right? I mean, it's a single use plastic. Wouldn't it be awesome if we could make planter pots where you take that tree, you dig the hole, you put the whole thing in the ground, cover it up, and you're done? And so is it economical? I don't know. We've explored opportunities. I know we can make it. The concern is you sort of think through the business strategy. If I'm, some of these companies that, the big nursery providers, right? That pot needs to survive, needs to be resilient, robust enough that people are throwing it up into trucks, right? Loading up trucks to haul trees across the country. And then, it's got to be able to stand the travel.
Yeah, strong enough to get to the consumer.
Yes. But if we can get there, which I think we can,
it'd be a great alternative.
Oh, it'd be awesome.
That would be so cool. Like trash bags.
Yep.
That would be a great thing to do. I mean, how cool would it be to have a plastic trash bag filled with other biodegradable plastic products and basically it goes there and it just all disappears.
Yep.
They were talking a little bit at that meeting about how it probably won't end up going into the food industry because even though it's completely sterile, the stigma with it, it's just people don't want to think about fecal matter close to their food, even if it's sterile.
And I have a funny story to tell about that. So on one of my research projects, we were doing some STEM outreach to a 5th grade class here in town. And so we were teaching them science, and it was great. I took a bunch of my grad students. And so as we were sort of, several weeks doing this, winding down, I brought in some bioplastics. So I gave them my little glad baggy material, and I had them pass it around and check it out. And I talked to them a bit. Then I got it back. And one kid said he could smell dairy. He could smell the manure. And I was astounded at that, right? Because I can't, right? But to think that it's gone through all of this, fermentation, storage by the bacteria, purification with chloroform and other solvents from the bacteria, and he could still smell it. So, to your point,
I wonder if it was just like a placebo effect kind of thing.
But I hadn't said anything.
You hadn't
really
what it was made of?
No, I had not.
Oh, wow.
That's my mind.
Oh.
Yeah,
well,
I had not said anything. A 5th grader, right?
I was going to say, if you had told him beforehand, then maybe like, he just...
Wow.
If he...
No.
Well, even with it not being involved in single-use food production, that kind of thing, there's still tons of other uses. Oh my gosh.
Think about disposable razors.
Yeah.
Right? I mean, nobody's going to care about that. Obviously.
Or even, I guess you're putting that in your mouth, but I was thinking about flossers.
The floss
I use these biodegradable bamboo flosser things because I hate throwing so many of those away.
Yeah.
So maybe not that for the manure, but I mean, I don't know. Would you use it? See, you make it.
Yeah,
So.
no, I know that it's not anything like what we input into it. It's a lot
But
cleaner. It's sterile, but it's just the thought of it. I mean,
yeah.
I mean, maybe it's not for me. Some people may use it. They may be fine with it.
I mean, people are okay with oil, so.
We take a plastic bottle that's made from oil and we put that to our mouth, right?
Yeah.
Yeah.
But no, I agree with the perception, and that is definitely not the target. We're definitely going to be looking at easier entry products that people are going to embrace.
So, along with the public perception, how do you think this will change the public's view of the dairy industry by changing manure into bioplastic?
If we can help the dairy industry, through technologies like this, continue to increase their profile in a positive way, that's a good thing, right? If the public can see that they're investing in the Idaho Dairymen Association, Bob Nearabot, Rick Nearabot, and that group have supported our research. If they can see that the industry is trying, which they are, that's a good thing, right? I mean, just not vilifying them, right? Nor should they be, right? So, and then these are hard. Running a dairy is, I can only imagine, it's insanely difficult.
Definitely. Yeah, you're very much at the whims of just the market and everything. I feel like most of it's breaking even, and it is 24/7. It runs constantly.
Need to be attended to all the time,
yep.
Right? I mean, it's. I would imagine being a dairyman is extremely difficult, right? And if we can develop a technology to help them manage their waste, generate some revenue streams, right, and raise their sort of public, their profile.
Yeah, and even address the carbon neutral by 2050 promise that the dairy industry made. I mean, that's a huge goal to have,
mm-hmm.
and that'll help tremendously. It's one of those things you have to spend years testing before it gets its feet off the ground. So hopefully by that time, things will be shifting in a more economical but also sustainable way.
Well, I think about the bioenergy side too. I mean, I know anaerobic digestion is not seen positively in the dairy industry, and I understand why. But that technology produces a lot of valuable energy, right? And as we look to wean ourselves from coal and natural gas, right? Bioenergy from anaerobic digestion or dairy manure, I think needs to be part of the equation somehow. It's not an inconsequential value, right? And at some point, and we're seeing this at wastewater treatment plants. There are treatment plants that are energy neutral. Gresham, Oregon is energy neutral because they import organic waste and they anaerobically digest it and they burn the methane to produce electricity. It just needs to be packaged. Right? I think that part of the challenge is it was just anaerobic digestion in the dairies.
Yeah.
Right. And that wasn't enough. It needs a restart with a more diverse portfolio of products, including bioplastics.
Yeah, definitely. I think just closing that loop, that circular bioeconomy loop, mm-hmm. will help add more value to anaerobic digesters, mm-hmm. and hopefully make it cheaper by feeding other things in and mm-hmm. kind of make everything work together seamlessly. That's the hope.
And there are other folks on the ground, doing the biochar piece, right? I mean, there's an integration to be had there. Right. I don't think we're going to get to the clean water side. I mean, that's a significant investment of energy. I mean, we know as environmental engineers how to produce clean water from very, very dirty water. But is it economically, useful?
Yeah.
Right.
I guess let's get personal. What motivates you about your research with this?
Lots of motivations. And I would say this even if he wasn't sitting here. But it's working with bright young people like Brandon. Right, Colton. I could go down the list of all my grad students, past and present. It's fun, right? Working with young people keeps me young. So
I don't think it's us. I've seen you up in the line. Yes. I think you're a kid at heart.
Yeah, I am. But there is something to be said about working around 20-somethings all the time, right?
Yeah.
I've got lots of grad students out there doing, wonderful things. That's rewarding, right? I also like the science part. I like the science and the engineering. It's my wife teases me. She says I play with poop, and I always try and clarify. It's like, no, I do a lot of microbiology, molecular biology, biochemistry, engineering, right?
You're like, it's so much cooler than just that.
It's this complex problem that's highly dynamic, hence the machine learning piece, right? And how do we develop solutions that make things better in the future? It's a problem. Engineers solve problems, and I like that. And I like what I like about the environmental engineering side is there's no recipe, right? It's constantly changing, and so the knowledge that you have to develop and constantly evolve is exciting too.
What do you guys envision for the future for biodegradable plastic made from manure?
As far as envisioning, I think that we can both say we hope it gets outside of the lab. We hope it becomes something. A plus would be economical. Obviously, it need to be economical for something to be implemented. But just being able to help the environment and take away some of these negative impacts that we mentioned throughout today, the oversaturation of phosphorus and nitrate, the reliance on fossil fuels for our plastics. I mean, if we can get something out there that, obviously Dr. Coats has put a ton of time into, and it's kind of been with him all his life since his PhD, and have a meaningful impact on the environment, it would be substantial.
Yep, be a great legacy.
Yeah.
And it'd be awesome to help the dairy farmers, right? To contribute to another industry.
That's such a cool thing to be a part of. Even me, I'm not even like doing your guys' research, but just to talk to you and be involved with the ISA grant is really neat.
Mm-hmm.
I feel like we're making an impact, definitely. And yeah, I hope it does make it out of the lab.
Yep.
I think it needs to. It's too cool not to.
Yeah. Well, I think, so I'm on sabbatical next year, and part of my sabbatical plan is to do some business planning. It's one of those things where I don't want to leave it. I came from consulting before I went into academia. So I'm very much on the, scale things up, build big infrastructure, things, solving problems in communities and society. I don't want to just retire and leave this in the lab. That would feel, I'd leave an empty feeling, I suppose. Right.
Yeah.
I really like where we're at. I think with the work that Brandon's doing, and I just dropped the machine learning on him last week, but he knows I'm excited about it. And I think we both agree there's real potential there. And then I'm excited to see this big push we've had over the past 6 weeks, what Colton's, thesis looks like. It's really getting to that. How do we predict? How do we predict an outcome, right? How do we take a culture of bacteria? How do we test them, and how do we predict what they might be able to do? And that's Colton's thing. And then the real-time process monitoring that will train a model and get it to a scalable.
I think it's very exciting too, because I think some people may look at it and say, oh, it's just nature, that's bacteria, they're going to do what they do. But we have all these other processes like struvite production, stuff in wastewater treatment plants. It's just a matter of finding the right indicator to be able to predict and have it be reliable.
Plus, just working around poop is kind of halfway in the game. Everything's funny in our lab. Right?
I bet there's tons of poop jokes and stuff.
Oh,
you should go upstairs into our lab manager's office. There is a wall or 2 walls covered.
If anything just goes wrong, you're like, ah, shit. And you're like, aha, that's funny.
Exactly.
How's your work? It's a shitty job.
Exactly, right? So everything.
I've heard dairymen say that too. There's always manure everywhere.
I'm pretty sure when I went down for the ISA meeting, I forget his name, but the first place, I'm pretty sure he made that exact joke.
Oh my gosh. That's funny. Do you have some bioplastic in your lab? I would love to just hold some. I've heard so much about it. It'd be cool to actually see some in person.
In my office, absolutely.
Oh man, this is just so cool. The whole idea of it.
I think it's very exciting that he does have some, actually being able to. It's fine in theory saying, they can make this, but actually having a product made from it, like the baggie, and being able to see, hey, this is
Was that the first thing? Was that the first thing you made from it? Is a bag?
We made some composite products. So we blended it with wood flour, Sort of like Trex decking, right? There's also sorts of composite products where they take, petroplastics and mix it with wood flour, wood fiber, right? So that was one of the first things we did, right? And that's where I got thinking about the planter pot.
I think in your presentation, did you talk about making like a spoon or something? I don't remember.
I probably would have steered clear of that. I mean,
It was something. I don't know.
We've talked about 3D printing, that sort of a thing, right? If we can purify it and produce something.
Oh, yeah. That's huge. Yeah.
Yeah.
Oh,
so we
man.
get to a raw material that would be amenable to 3D printing.
Yeah.
Right. But that's, again, Armando McDonald, polymer chemist, I just sort of
that would be so cool.
Yeah.
And that's something that could be later like explored too after this is like off the ground and stuff.
Key thing is to get into the market, be at a point that it's at least break even, maybe a little bit of profitable to support R&D, and then evolve the products from there. We're not. I was advised a long time ago: don't seek perfection. Right? If you're trying to get to perfection in the research, it's going to live in the lab forever.
Yeah,
so
definitely.
And so that's the business plan. Part of it. And I think coming from consulting as I did, I mean, I'm not an expert in business, but I'm a little atypical academic. I think that's kind of where we're at, right? So I'm happy to show you some of the material we have, take some pictures or whatever.
Well, thank you both for taking the time to tell us more about Manure-made biodegradable plastic. After the interview, Dr. Coats showed me his legendary bioplastic, and I got to hold it in my hands. It's amazing hearing so much about something and then actually having it in front of you. And yes, I did smell it, and it didn't smell like manure at all. I want to thank you all for joining us for this fascinating episode of the Clever Cow podcast. We've had a great time discussing the incredible research by Dr. Erik Coats and his team on transforming dairy manure into biodegradable plastic. Their innovative work is truly paving the way for more sustainable dairy practices. Before we wrap up, I want to give you a sneak peek into our next episode. I'll be sitting down with University of Idaho economist Hernan Tejeda, another key member of the ICED grant team. We're in for a fun and insightful discussion on the economics of sustainability, the intricacies of carbon credits, the pressures facing the dairy industry, the rise of robotic milking, and so much more. You won't want to miss it. To stay updated on our latest episodes and all things related to the ICED grant, be sure to follow us on social media. We release new episodes every month, and we also welcome your questions and comments. Your feedback is invaluable as we explore the future of sustainable dairy together. Thanks again for listening to the Clever Cow podcast. Until next time, stay curious and keep supporting sustainable dairy practices.